Alright, this is Thermochemistry, Chapter 11, and let's get right on to it. So the bell work here was asking us about solids, liquids, and gases, and looking at the particles within them. And so let's go through it. The amount of movement of particles in a solid, it's not none, it's actually a little bit. So in class I had written a tad. Just a little bit of movement, but the particles are tightly bound together. In a liquid, there is some movement. The particles can slide past each other. In a gas, there is a lot of movement. Okay, so the amount of movement and the amount of energy are actually correlated. So I just had everybody draw arrows down, about the same. The example of a substance could be anything for solid. Common answer in class was desk. Liquid, I said other than water. And someone gave me apple juice. We'll use that one. Apple juice. And then gas, something other than steam. Some people put methane or oxygen or carbon dioxide. Particles in a substance. So with solid, you would have drawn something similar to this, where everything's tightly packed. Liquids, there's a little more movement of the particles, and then gas, very, very spread out. So one of our first definitions here was thermochemistry. What is thermochemistry? Well, thermochemistry is concerned with heat changes, okay, that occur during chemical reactions. Also could be a physical process, something like boiling or freezing, okay, but we are concerned with the heat changes. So this is our first instance of energy so far in this course, and energy is the capacity for doing work, or in this case, we're going to be looking at supplying heat, whether it's to a chemical reaction or from a chemical reaction. Energy comes in many forms. Two generalized topics are kinetic energy and also potential energy. Now, kinetic energy is the energy of motion, whereas potential energy is the stored energy. So down below, not only can you have potential energy that's stored up in something like a ball that's held high and it's about to be dropped, you can also have potential energy in fuels or foods. So gasoline is a type of fuel, and it has potential energy, and that potential energy is released as the bonds are broken by ignition or combustion in the pistons of the engine, which eventually turns the wheels of the car and produces kinetic energy. So a student is heating water to cook pasta. She noticed that it begins to boil at a temperature of 100 degrees. What is the temperature of the water if she keeps boiling it for 15 more minutes? Well, 100 degrees Celsius is the boiling point for water. So if you keep boiling it for 15 minutes, the water will stay at 100 degrees Celsius. Okay, because anywhere past 100 degrees Celsius, it's going to become a gas. Okay, it's going to turn into steam. So no matter how long she boils, she could boil it for an hour and a half, it'll still be water at 100 degrees Celsius, because anything past that is a gas. We are looking at a few different examples, and we are going to label whether each is potential energy or kinetic. The first one, a stretched rubber band, that would be elastic potential energy. A cookie, that would be chemical potential energy. A glass sitting on a shelf would be gravitational potential energy. And then a falling leaf, well, if it's in motion, it has kinetic energy. A lot of people think that heat is just temperature. Well, in this case, we look at heat. Okay, this is a new vocabulary word. It is energy that is transferred from one object to another. So it's not just putting a thermometer on something and measuring heat. That's not the case. It's an energy transfer from one object to another. So heat always flows from a warmer object to a colder object. Just like in biology, with osmosis, you had a concentration gradient where solute would flow from high concentration to low concentration. In the last unit with gas laws, we saw the pressure gradient, where you had pressure wanting to go from high to low pressure. Here, we look at heat, and it goes from a warmer object to a cooler object. Heat cannot be measured directly. So, we are going to learn an equation that we can use in order to calculate the heat, but it can't be measured by just one measurement, okay? We have to take into account several different variables. To start observing heat, we need a point of view. And so in chemistry, we use something called the system's point of view. The system is the part of the universe on which you focus your attention. So we pick something that we want to observe the heat change within. And once we pick that, everything else is called a surrounding. Okay, so in this case, in this example over here, we have a test tube. And we have identified that this test tube is our system. So we're only concerned with the heat changes within this test tube. Okay, everything else around here is the surroundings. All right, so it looks like in this chemical reaction, we are going to have heat from the test tube released into the surroundings. The system is releasing heat into the surroundings. The law of conservation of energy is similar to the law of conservation of mass. Energy is neither created nor destroyed. It only changes forms, whether it's a chemical or physical process. So, we're looking at the test tube in the last slide. The heat can be lost by that system, okay, but it's not destroyed. It's just transferred out to the surroundings. For instance, the guy's hand that was holding it, the air around it, okay, the test tube clamp that was holding it. We have two words here, endothermic process and exothermic process. You may have learned these before. Endothermic process does not just mean something that is cold. There's much more to it. Same thing with exothermic. It just doesn't mean that something's hot. We have to go a little bit deeper for that. So in this case, we look at endothermic process, and that is a system that absorbs heat. Okay, endothermic processes absorb heat. Exothermic do the complete opposite, and they release heat. So technically, when something absorbs heat, the surroundings are going to feel cool. And in an exothermic process, when something releases heat, the surroundings will feel cold. So we're going to label these as exothermic or endothermic. Evaporating alcohol. Okay, before we do these, I want to point out that if we are going up, okay, in energy through a phase change, okay, if we're going from a liquid to a gas, we are going to have to absorb energy. The water, let's take water for example. The water will have to absorb energy to go from a liquid to a gas. And if that is happening, if we are absorbing, which we learned on the last slide, we call that an endothermic process. Okay. If we are going the opposite way, if we are cooling, going from a gas to a liquid or a liquid to a solid, in order for those molecules to cool off, they have to release heat into the environment. So that would be exothermic process. Okay, so if we go from a liquid to a gas, we would say, oh, well, the gas is being heated up. It's hotter than a liquid, so that must be an exothermic process. Well, that's not the case. The liquid has to absorb heat in order to shoot off into the gas phase. So let's look. Evaporating alcohol, well, if we are going from a liquid to a gas and we are evaporating, that is an endothermic product. Let me use a red pen. So endo. Burning. If we are burning something, okay, anything that is on fire or combusting, that will be an exothermic process. Heat is being released into the environment. Boiling water, we are going from a liquid to a gas, so that would be an endothermic process. If we are cooling water, it has to release heat in order for the particles to cool down, so that is going to be an endothermic process. Excuse me, exothermic. Melting ice, if we're going from a solid to a liquid, that will be an endothermic process. Freezing water, that would be an exothermic. So just like the gas laws that we covered last unit, we were looking at different units for pressure, such as kilopascals, atmospheres, torrs, millimeters mercury. So with this topic, with energy, we want to look at the units associated with them. So we have two. We have the calorie and we have the joule. Two different units here, but they both express energy. So let's look at the first one. A calorie is the quantity of heat needed to raise the temperature of 1 gram of water, 1 gram of water by 1 degree Celsius. So the way I described it in class was that if you have a cube, oh, that is bad. If you have a cube of water, there's water in that cube, the heat that it would take to light that cube of water, by 1 degree Celsius, that's how much energy it would take, is 1 calorie. So on the right, we had used the comparison of what if you actually broke all the bonds in the chemical compounds of these foods and put them into something we could see. Energy use. What could we heat up, or what could we power? 5 pounds of spaghetti would heat up a pot of coffee. A piece of cheesecake would heat up a light bulb for 1.5 hours. And if we were able to convert the energy stored within 217 Big Macs, well, we could drive a car 88 miles. So this is just showing that there is energy within chemical bonds, and once they are broken down, they can be produced into work. Now, don't go put 217 Big Macs into your car. It doesn't work like that. But the energy equivalent is the same. There is a comparison or a conversion that you can use here, and it is 4.18 joules is 1 calorie. So if you want to convert units from calories to joules, use 4.18 as the conversion factor. With pressure, we use conversion factors like 101.3 kPa is 1 atm, which is 760 mmHg or 760 torr. So something that might seem confusing, because, hey, in science we like to be confusing. A calorie with a capitalized C is what we use on nutritional labels. So it's capitalized, and this doesn't make sense, but what we want you to know is that this calorie with a capitalized C is actually 1,000 regular calories that we'll see in class, that 1 calorie with a capitalized C equals 1 kilocalorie. Why they don't just call it a kilocalorie on your food labels, I don't know. I would love to find out. I may look it up later. So for instance, if we have a candy bar and it is labeled with 180 big calories, that's really 180 kilocalories or 180,000 calories. So just be mindful of that. If you're looking at a nutritional label, it's not actually 180 calories that we would see in chemistry class. It's 180,000 calories. So for instance, another quick example, you would have, let's see, use my highlighter here, calories up here, there are 690, but it's the capitalized C. So instead of just 690 small calories, like we would see in chemistry class, it's actually 690,000 calories that we would see in class here. Another vocabulary term that we want you guys to understand is heat capacity. It's the amount of heat needed to raise the temperature of an object 1 degree Celsius. It depends on mass and composition. So you guys might say, oh, well, that sounds like a calorie because we had just talked about heating up an object by 1 degree Celsius, a cube of water? Well, it's similar, except heat capacity deals with any object, and it also depends on the mass and composition, so like the density of the object. Water has a high specific heat. Water has a specific heat value of 4.18 joules per gram Celsius, and we'll look at that in more examples later. Okay, but if something has a high heat capacity, that means it's going to take a lot of energy to heat that object up, or it's going to take a lot of energy to cool that object off. Okay, so for instance, if you're looking at just water, it's going to take a lot more energy to increase the temperature of a large pot of water, think of a pool, rather than a small cup of water. And that makes sense. It takes more heat to raise the temperature of water than metal. So a lot of people don't think that well. They think, oh, well, it takes a lot more energy to heat up metal than it does water because metal's tough and it's hard and it's a metal. Well, that's not always the case. Water has a high specific heat. Okay, keep that in mind. So it takes a lot more energy to heat that up than it does the metal. In coastal areas, that's why the temperature doesn't change a whole lot. It fluctuates very moderately because water doesn't like to change heat very well. Okay, it takes a lot of energy to heat up coastal areas, and it takes a lot of energy to cool off those coastal areas too. So that's why the temperatures don't fluctuate a whole lot. With something like aluminum foil, okay, aluminum's a metal, you could heat that up in the oven for an hour, take it out, and 5 seconds later, the aluminum foil is cool. It's got a very low heat capacity.